Good morning, everyone. My name is P. Sharanteja from CSC Today I will be presenting the topic Face Center Cubic FCC Crystal Structure. This concept is important because crystal structure directly affects properties such as strength, ductility, melting point, conductivity, and application suitability in engineering. Introduction to crystals structures. To understand FCC, we should first understand what is a crystal is. A crystalline solid consists of atoms arranged in repeating and orderly of three-dimensional pattern called crystal lattices. Examples of crystalline solids include metals Cu, Al, and Fu. It means copper, aluminum, and iron. Salt like NaCl and diamond. In contrast, amorphous solids like glass and plastic do not have long atomic order. The repeating smallest building blocks is crystalline materials is called unit cell. There are 7 crystal systems in the solid state physics. Are among them are the cubic system is one of the most important because many engineering materials follow it. Within the cubic system, we have simple cubic SC, body center cubic BCC, face center cubic FCC. Among these, FCC is the most densely packed and mechanically favorable. Definition of FCC. The FCC, the center cubic, the crystal structure is a type of cubic lattice where 8 atoms are located at the corners of the cube. 6 atoms are located at the center of the face. Because of these, atoms are arranged very closely and efficiently. FCC is also known as cubic close packed structure. FCC have highly packing efficiency, which leads to high metal density and mechanical flexibility. FCC unit visual represent an atom count. Let's calculate the number of atoms per unit area in FCC. Each corner atom contributes 1 by 8 to the cell of 8 corners into 1 by 8 is equals to 1 atom. Each center phased atom contributes 1 by 2 means 6 phases into 1 by 2 is equal to 3 atoms. So in total 1 plus 3 is equal to 4 atoms per unit cell. This is higher than the BCC. 2 atoms and FC is 1 atom and making FCC structures are more compact. Atomic packing fraction. So the atomic packing factor tells us how much space inside a crystal is occupied by atoms. APF is equals to volume of atoms in the unit cell by volume of the unit cell. For FCC, volume of 4 atoms is equals to 4 into 4 by 3 pi r cube. Unit cell volume A cube is equals to 2 into root 2 r whole cube is equals to 16 root 2 2r cube. So APF is equals to 4 into 4 by 3 pi r cube by 16 into root 2 r cube is equals to 0.74. So 0.74 means 74% means FCC is extremely space sufficient. Only hexagonal close packed matches the APF. So the edge length is equals to A and atomic radius is equals to R. Relation between A is equals to 2 into root R. Volume of 4 atoms is equals to 4 into 4 by 3 pi r cube. Volume of cube is equals to A cube is equals to 2 root 2 r whole cube is equals to 16 root 2 r cube. So APF is equals to 4 into 4 by 3 pi r cube by 16 root 2 r cube is equals to 0.74. Coordination number. The coordination number represents how many nearest neighboring atoms are directly contact with the single atom. For FCC, coordination number is 12, which means every atom touches 12 other atoms, a strong indicator of dense packing, leading to high malleability, high ductility, better metallic bonding. This is one of the most reasons metals like gold, copper can be drawn into thin wires. They are also good thermal conductivity and highly corrosion resistance, and they also have strong metallic bonds between them. Relation between the relation between the atomic radius and lattice constant. In FCC, atoms touch along the phase diagonal, not along the edge. If radius is equals to r and lattice constant is equals to a, 4r is equals to root 2a, which where means a is equals to 2 into root r, root 2r. The relationship is used in density calculations and X-ray diffractions and material characterizations. Understanding this helps the engineers to determine atomic spacing and mechanical behavior between the metals. Examples of FCC metals. Metals like aluminum has atomic radius of 143 and density is equal to 2.70 grams per centimeter cube, and remarks are lightweight and ductile. Metal like copper has atomic radius of 128, where it contains density of 8.96 gram per centimeter cube, which is excellent in conductor. Metal like Au has atomic radius as 144 pm and density is 19.3 gram per centimeter cube, and it is very dense and malleable. And metal like Ag has 144 pm and density 10.5 density per gram per centimeter cube. Remarks are highly conductivity. So the applications of aluminum are it is used in my aircrafts, packing and automotive. Copper is used in electrical wiring. Gold Au electronics and jewelry. Silver Ag conductivity and optics. Metal like nickel has applications like stainless steel alloys. Because FCC metals are ductile and deform easily, they are widely used in industries requiring workability, flexibility, and corrosion resistance. Properties of FCC metals. FCC metals have 12 independent slip systems. A slip system is a combination of slip plane, preferred plane of deformation, slip direction, direction along which atoms slide. FCC 6 flip system, 111 and 110. High number of flip systems means FCC metals deform rather than the fracture. They maintain structure under cyclic loading. There are idling for forming and bending and rolling and execution. This is why aluminum foil can be folded many times without breaking. Content. FCC metals are highly ductability, can be easily drawn into wires, and also they are good thermal and electrical conductivity. Highly packing efficiency means which has highly density. It means it is very so much denser. The flip systems are 12. Metal deforms easily under the stress. FCC versus BCC versus HCP. Property of FCC. APF is equal to 0.74 and ductability is very high in FCC metals, and flip systems are in FCC are 12 systems, and density is so high in FCC, and core brittleness is nothing. And properties in BCC is APF is equal to 0.68, ductability is medium, and slip seasons are 48 but inactive at low temperatures. And in BCC, density is very medium and core brittleness is there. So FCC is the best for forming and shaping of operations. FCC structures are firstly established using X-ray diffractions by physicists Max von Wiew and W.H. Bragg and W.L. Bragg. Their work helped solidify their field of crystallography and earned Nobel Prizes. FCC has one of the eldest metal structures to be discovered. In FCC, nanoparticles like gold are having high surface area and they are excellent in calistic properties and are used in sensors and improve the battery capacity and are stable against structural collapse. FCC gold nanoparticles are also used in cancer detection and targeted drug delivery. FCC metals remain ductile even at the low temperatures. In contrast, BCC metals become brittle in cold conditions. FCC metals stay soft and workable. This is why aluminum alloys are used in Microsoft and cryogenic containers and refrigeration systems. Temperature does not reduce slip capability in FCC metals. So that's why FCC is the best for forming and shaping the more in operations. Conclusion and summary. To summarize, FCC is phase center cubic structure which contains 4 atoms and unit cells. APF is equals to 0.74 which means 75% of highly packing efficiency and the coordination number is 12. FCC metals are highly ductile and strong and corrosion resistant. Used in aerospace, electronics, energy and biomedical industries. FCC is nothing but strength plus flexibility plus standability. Thank you.